All right, so this video is just supposed to be a quick math review for the math you'll need for Physics 7D. Now, obviously, I can't cover all the math that you'd need for this class, but I'm just gonna go through the main things that we use the most and common mistakes that people make. So, throughout this course, there will be very, very common mistakes that students make every single quarter. So I'm gonna try to point some of those things out so that hopefully when you're taking exams, you'll be conscious of that and not make those mistakes. So the first, sort of basic thing that people make a lot of mistakes on, this is actually the number one mistake when we do chapter 22 and we do Gauss's law. The number one thing I end up taking off points for in Gauss's law is not knowing your area and volume formulas or using the wrong one in the wrong situation. So these things are not on your formula sheet. I absolutely expect you to know the formulas for the circumference of a circle, the area of a circle, for a sphere, for a cylinder. Those are things that you absolutely have to know, whether you're a physics major or a math major or an engineering major, you absolutely need to know the formulas for the circumference and area of a circle and sphere. So the circumference of a circle is 2 pi r, the area is pi r squared. Again, when we do Gauss's law, the number one most common mistake is switching these two things. So please make sure you memorize circumference and area. Then for a sphere, so when we're in 3 dimensions and we have a sphere, the surface area of that sphere will be 4 pi r squared, and the volume will be 4/3 pi r cubed. We're going to be using this formula a lot, again, when we do Gauss's law in chapter 22. And then we're also going to be using the surface area of a cylinder a lot. So for a cylinder, if I have, let's just say a cylinder here, it has length L and it has radius R. The surface area of this cylinder will be the surface area of the top and the bottom. So each of those will be pi r squared. So you have 2 pi r squared. And then the side area here will be the circumference of the top circle times the length of the cylinder. So you'll have 2 pi r times L, and you add those two things together, and that's your surface area. Now, we'll be typically either using just the top and bottom or just the side. We're not going to really be using the surface area of a whole cylinder. Okay, and then the volume is just the area of one of either the top or bottom, and then times the length, and that will give you the volume. So it's going to be pi r squared L. Okay, so that's just some basic formulas that you need to know. Now let's go on to just scalars and vectors. So a scalar is just a number. It has only a magnitude. A scalar can be positive or negative. And the classic examples of scalars are temperature. Temperature is just a number. It has no direction. Temperature, speed, distance, those are all scalars. Since they don't have a direction associated with them, they're just a number. Now vectors have magnitude and direction. So velocity, acceleration, force, those are all examples of vectors. And it's important to note here also that when we talk about the magnitude of a scalar, that just refers to the absolute value of the scalar. So even though temperature can be, negative 20 degrees, the magnitude would just be 20. So if you see, but usually we don't really refer to the magnitude of a scalar. It's usually just referred to for vectors. Okay, so then the components of a vector. So we know that vectors, if we have like a coordinate system here in our x and y components, we know that our vector, let's call that v, will have some angle here, and then it will have some y component and some x component over here on this side and this side. Now obviously you could have also a vector in 3 dimensions, so we'll be doing a lot of that. So if we have our x, y, and z directions, you could have a vector that, sort of comes out and is like this and has a component in each of the 3 directions. So now if we want to break a vector up into components, a lot of you have seen, I'm sure, that x equals r cosine theta and y equals r sine theta. Now that's true, but only sometimes. So this is not true all the time. This formula is only true if your vector is set up like this in the normal, basically, configuration, sort of, or the normal way. So if your vector is set up so that its, angle is measured counterclockwise from the x-axis, that's fine. And your x component will be cosine theta because it's adjacent to your angle. and your y component will be r sine theta because it's opposite from your angle here. But if you, let's say if we set up, or we have a vector like this. So let's say our vector is actually going in this direction, and let's say we have this angle here as theta. Well, now on our y side, remember SOHCAHTOA. So you can see that cosine goes with the adjacent side. So the adjacent side of our triangle here gets r cosine theta. So now r cosine theta is actually giving us the y component of our vector. And the opposite side from theta is r sine theta, because sine theta is sine equals opposite over hypotenuse. So the opposite side from our theta gets the r sine theta. And now we can see that sine theta is actually the x component and cosine theta is actually the y component. So I would say just forget this. So don't ever think about this again. And just think about SOHCAHTOA. So just think in terms of opposite and adjacent sides. Your adjacent side to your angle always gets the cosine. Your opposite side to your angle always gets the sine. Because this trips a lot of people up. This isn't true all the time. It depends on how your triangle is oriented. So just think in terms of SOHCAHTOA, and that way you won't make a mistake. Okay, so that's some basics about components. Now, the magnitude of a vector, like I said, just refers to the vector's length. So that's why this is always positive, because you always have to have a positive length. You can't have a negative length. And the magnitude of a vector is calculated using the Pythagorean theorem. So if we have a vector in 2 dimensions, it would just be the x component squared plus the y component squared. So this quantity always has to be positive, obviously, right? There's no way to get a negative number from this. And then in 3 dimensions, you would just add in your z component there, and that would be your magnitude in 3 dimensions. So again, if I have a vector, this is x and y, and my vector is like this. This is the magnitude of my vector. It's the length of this arrow. So if my vector goes to this point, my magnitude is just the length of this vector from the origin to that point that my vector points to. Okay, so now just some basics about how to write vectors. So we've seen our unit vectors here. So our unit vectors, we can call it x hat or I hat, and that is just a magnitude 1 vector where it just has one component in the x direction, and then the other 2 components are both 0. Then our y hat or j hat vector, we have just a vector of magnitude 1 in the y hat or j hat direction, and 0 in the other 2. And the same thing for z or k hat. It's just magnitude 1 in the z hat, and the other 2 components are 0. And then when you write out your vectors, you can either write it in terms of like these parentheses where you have your x component, y component, and z component all separated by a comma, or you can write them out as the x component in the x hat direction plus the y component in the y hat direction plus the z component in the z hat direction, or you could write it in terms of I hat, j hat, and k hat. It's all the same, it's fine. The only thing is don't do both. So I see a lot of people where they'll write it with the parentheses, but then also insert the x hat, y hat, and z hat. So that's not correct because it's formalized. Like our notation indicates that this is the x direction, this is the y direction, this is the z direction. So there's no need to input the x hat, and it also just doesn't really make sense with the way like we sort of formalize how we work with vectors. If you write it this way, x hat is a vector like this. So you're sort of like inserting another vector into your vector. So it doesn't really make sense from that perspective. So just stick with one of the 2 ways. And this is not correct, so don't do that. Okay, so now let's go into the dot product. So we're going to be using the dot product a lot in this class. So the dot product, the important thing to remember about the dot product is that it takes 2 vectors and returns a scalar. So your dot product always ends up being a scalar with no directions, just a number. So to do a dot product, or to take a dot product, we have one vector, we'll call that vector A, and then we have our second vector, vector B, and you just multiply the corresponding components and then add them up, and that's it. So just the x components of each vector multiplied together, plus the y components of each vector multiplied together, plus the z components of each vector multiplied together. And this obviously will give you a scalar. Or you could do it this way. You could write it as the magnitude of the a vector times the magnitude of the b vector times the cosine of the angle between them. So I would recommend really only using this when you have a vector that's in only 2 dimensions. Sometimes when you go into 3 dimensions, the angle between them is not obvious, and it's very easy to make a mistake because you might only be looking at the angle taking into account only the x and y hat components, not taking into account all 3 directions. So be careful if you're in 3 dimensions that you're using the correct angle between them. So I'll try to draw a picture. So let's say if I have x, y, and z, and let's say that I have this vector. So this vector is kind of, it's in all 3 directions here. So there's like an angle here, and there's like an angle here that it's at. If I want to find the dot product, let's say I have a vector that's totally in the z direction here. The angle between these is like angled in all 3 dimensions. It's not like a simple angle where it's just in the x and y plane. It's in the plane sort of between these 2 vectors. So it's not obvious what that cosine is. So that's why when you're doing it in 3 dimensions, be really, really careful that you're actually using the correct angle. It's very easy to make a mistake that way. I'll try to find a better picture when I upload the notes. Obviously, I can't really draw in 3D that well. So that's our dot product. Now I just want to do a little bit of where the dot product is a maximum and a minimum. So the dot product, since let's look in, this is our vector A and this is our vector B. Let's use our cosine formulation. Since we're only in 2 dimensions right now. So when these 2 vectors are at a right angle, theta is 90 and cosine of 90 is 0. So the dot product of 2 perpendicular vectors is 0. And the way that I sort of think about the dot product is it tells me how much the vectors sort of overlap. Are they in the same direction or not? So if the vectors are in totally different directions, if they're in perpendicular directions, they don't share any components. There's no overlap between them. So the dot product is 0. Now the other case is if, let's say my 2 vectors are parallel. So AB cosine. Now the cosine, the angle between them is 0 degrees because they're parallel, so they have no angle between them. So now this means that the dot product is just the magnitude of each vector multiplied together. So this is the maximum that you can have. So this is the maximum possible value of your dot product for 2 vectors A and B. So the dot product is a maximum when our vectors are parallel. And then another sort of limiting case is when our vectors are in opposite directions. Now the cosine, the angle between them is 180 degrees because they're anti-parallel. So the cosine of 180 is -1. So the dot product is -a times b. So this is the minimum value our dot product can take of 2 vectors with lengths a and b. So we're going to be using the dot product a lot. So definitely make sure that you're comfortable using the dot product and you understand. Basically, the most important thing is to understand that it's 0 when the 2 vectors are perpendicular, and it's either at a maximum or a minimum when they're parallel or anti-parallel. All right, now the cross product we're going to use quite a bit as well, but that will be more for the second half of the class when we do magnetism. So I'm going to, I do a review of the cross product, I think at the end of chapter 24. So I already have that planned out, so I'm going to skip the cross product for now since we do a whole thing of the cross product later. So let's go on to some basic calculus. All right, so I'm just going to go over like the most basic calculus because we're not really going to be using too many, I'm not going to be doing too many derivatives. we'll kind of just do some things where it's like find the derivative of like t cubed or t squared or something like that. So just make sure you remember the power rule. So this would be like 3t squared. So, just remember your power rule, where the derivative, let's say, of some function x to the n is equal to n x n minus 1. So that's pretty much the most common derivative we'll be doing. Also, we might be doing like some with the exponential. So like if we do e to the constant times t, or this will be a e to the at. So remember, for a exponential, you just basically move whatever constant is in front of the exponent here, you just move that down here, and then your function is the same. And then, for example, if this was negative, so like if we had d dt of e to the negative at, it would just be negative a e to the negative at. Okay, so that's some basic derivatives. Then we'll also be doing some u substitutions, but I'll go through that when we actually get to a u substitution problem for integrals. So just to remind you of basic, if we do a integral of x to the n dx, that will just be equal to 1 over n plus 1 x to the n plus 1 plus c. And then we will do some u substitutions. So I wouldn't really expect you, like I'm not going to ask you to do like a u substitution, like just, it'll just pop up in some random problem. There's just one specific integral that we do where you have to do a specific u substitution, and that's really the only one we're going to see. So as long as you just know the basics of a u substitution, then you just study that one that we do, you should be fine. The other integrals, so we're going to be doing some integrals that look like this, where we have like a closed circle on them. I'm going to go into those more when we get to them. So this is basically just a line integral. And we're also going to be doing surface integrals. But we're not really going to be doing line integrals and surface integrals, since they're all going to have a very high degree of symmetry, such that we can basically avoid doing an integral. So you'll see as we get to it, we're not really going to be doing any line integrals or surface integrals. Our formulas will just contain line and surface integrals, and then we'll cheat a little bit with symmetry so we don't have to actually perform any real integration. But I might do another video that goes into line integrals and surface integrals more deeply once we get to Gauss's law. Okay, so this is just a general review just to jog your memory of some basic calculus. And then partial derivatives. So partial derivatives, so we're not going to be explicitly using partial derivatives in the course, but they do pop up in the equations, especially if you look at other resources. A lot of, Maxwell's equations are formally written with partial derivatives. So partial derivatives are very easy though. So you'll see a partial will be written, like that. It'll just be like this fancy D. And all that means is you just take the derivative with respect to that variable, and all your other variables you just treat as constants. So if I wanted to just take, let's say I had a function where it was like x, y, z, t. So let's say I had 4 variables in my function, and I want to take the partial derivative with respect to t. I would just treat x, y, and z as a constant, and just treat t as the only variable. And what's the derivative of just t? Well, it's 1. So this would end up just being x, y, z. And that's it. So yeah, the partial is actually really easy. It couldn't really get easier. You just treat all the other variables as constants and take the derivative with whatever variable it says to right here. And that's really all there is to partial derivatives. So just for another example, if I had like the partial with respect to x, and my function was like, let's say x squared y cubed, my partial would just be 2x y cubed. And that's it. So the partial's, like I said, very straightforward. There's really not too much to it, at least at this level. Okay, so then let's go on to radians. So we're not actually going to use radians in this class, but almost nobody knows what a radian actually is, so I figured I'd go over it. So if I have a circle, So now we know that a circle has 360 degrees, and we know that a circle also has 2 pi radians. So what actually is a radian? Well, a radian is not equal to pi, so let's get that out of the way. So what is a radian then? So let's say I have my, I have a radius here. So this is the radius of my circle, and let's say I had like a length of string or something that was the length of one radius, and I laid it along the outside of the circle like this. So I just laid that one radius, so this little piece of rope here has the length of one radius. The angle that that makes would be 1 radian. So this angle here, whatever this angle is 1 radian. And since all circles have the same ratio of radius to circumference on every single circle, no matter how big its radius is, when you lay out the radius along the circumference, it will be equal to the same degree measures. So this angle measures, it measures 57.2 degrees. So about 57 degrees is 1 radian. And that's why the equation for the circumference of a circle is 2 pi r, because you can fit 2 pi lengths of your little radius rope. You can fit 2 pi radiuses around your circle, and that's true for any circle. And that's why a circle is made up of 2 pi radians. If you multiply 57.2, there's more decimals to it, it's about 57.2. But if you multiply that by 2 pi, you will get 360. And that's why the circumference of a circle is 2 pi r. Okay, so that's a radian, so I hope you'll definitely be using that in 7e, so I hope that helps. Okay, so that's it for just this math supplement. So yeah, I will see you guys next time.